have actual books.
Good, good.
Right, we're going to be live on YouTube in a minute.
Okay.
Hi, Andrea. Are you in Baltimore or Houston now?
I am in Houston now for 3 or 4 more days, then I'll go back to Baltimore.
Okay. All right. Okay.
In the summer, Baltimore is much nicer than Houston,
Yes.
as you well know. Yeah. Wow. Lots of
YouTube is working.
Very good. Ted, you may want to admit people who are joining. So I think you have the ability to admit all, right?
Everyone, the waiting room has been disabled, so everyone is joining now.
Yeah, I did that. Oh, we already have about 70 people.
Yeah, we have 70 people now. Yeah.
Hey, Rodney, how are you?
Pretty good.
Thanks
How
for
about you?
joining.
Yeah, so I couldn't miss it. Yeah, it sounds like a very interesting topic.
Hi, Rodney.
Hi, Andrea.
Hi.
How are you? How's Texas?
Well, it will soon be warm.
Did you get, and I assume you got vaccinated. Most people I know in Texas have been able to get vaccinated.
Well, I was spent the last few months in Maryland, and Maryland was behind Texas in vaccinations, but I did get vaccinated, so
okay,
that's good. Hi, Dvora. Hey, Yehuda.
I see familiar faces. Emilio is there. Emilio, good morning.
Good morning.
Yes, Emilio.
Greta, good morning.
Good morning. Those bubbles. I have to see them, you know.
Hi,
Emilio, how are you doing?
hi, Greta. Second time in a week.
Second time in a week, yep.
Good morning, Christian.
Hello. Good morning. Good afternoon.
Morning, everybody.
Nice to see you all.
Shu, how are you doing?
Good. Sleepy, but still awaking. Yeah. It's after midnight.
Oh my gosh.
Yeah.
That's what you get for being on the other side of the world.
The count is, we are 108 now.
Yes, 110 actually.
Yeah,
Yeah,
you're growing.
increasing rapidly.
Yeah.
Oops.
Okay, Andrea, in about 1 minute, I will get started. Would that work for you?
Sure.
So Ted, when I am making the introduction, would you admit people who come in? They're in the waiting room.
I think they get admitted automatically.
Oh, okay. No, I've been pressing it, but
Oh, okay.
Yeah.
Yep, I can do that.
Okay, very good. Okay, it's 11:30 my time, and let's get started. Before that, I need to first start recording. Very good. Good morning, good afternoon, and good evening, depending upon the time zone you're in. It's wonderful to see so many friends, if not in person, at least on Zoom. Can I make a request? Since it's going to be on YouTube, we would like only Andrea's face to show there. So if you don't mind, mute yourself and also turn off your video. In fact, I'm going to be muting all, And Andrea, remember to turn on your audio. I'm muting all of you guys. Okay. Very good. I want to welcome you all to the very first IJMF Spotlight seminar. We've all been affected by COVID in various ways. I think one particular area where it has affected scientific community and ours in particular is that we are not able to meet in person, discuss, debate, have coffee, tea, beer, or wine together, and have lively scientific discussion. So that part is missing. So we thought that maybe this IJMF Spotlight Seminar Series is a little way to address this problem, although it's in a very small way. So the idea is that this year and next year, we will have about a dozen to 15 seminars broken into a fall session and a spring session. So the spring session started a little late because we didn't get our act together in a rapid way. We wanted to also make sure that everything lines up. So this year it may be a little less than 15, but that's our hope. And the initial trial period for 2 years, which is 2021 and 2022. And if things go well, that we may continue or we may not. It all depends on us, okay? We can decide how we want to proceed. And the idea, as I already mentioned, is to bring up all of us. So from now on, feel free to sign in 5-10 minutes before, and we can chit chat for a few minutes. And then there will also be a Q&A session. So the interaction is the primary motive. Other than that, we want to promote the journal. IJMF is important to all of us. And we want to attract the best and the brightest, especially from the younger audience. And one way to do this is to promote the audience papers. Also, we want to promote the younger researchers in our community, showcase their outstanding papers. So one way to do this is that we're going to systematically look at some of the best papers that got published over the past year and invite them for this IJMF Spotlight seminar. Okay, so the idea is to generally people in their beginning and the mid-career is the one we're trying to target, but that should not be a limiting factor as well. Okay, the process is very simple. The editors will make the nominations. The community at large can also make nominations, but we rely upon our editors to tell us, hey, this paper reviewed very well and it's being cited a lot, things like that. So we want to identify papers that got published recently and pick the young author and showcase them. There's a selection committee. The selection committee consists of the 2 co-editors, myself and Alfredo. And other than that, Ted Heindel from Comfrey in the University of, Iowa State, and Shu Takagi. So it's a small committee, and we're going to decide who the speakers are for the initial round, and we can modify if the program, if the seminar series were to continue. And we're also a little ambitious. We want to have, we have about 170 people on the YouTube, but it's also simulcasted in, in Zoom, there are about 172 people, and there is also simultaneous YouTube live cast. I don't know how many people are watching that, and the whole thing will be available in a video format in IJMF website as well. Okay, and also I should mention that all the speakers will receive a plaque saying that they gave an invited seminar, so which they can display and they can put it on their resume. So just a little perk that we want to give. I want to point out that this is an experiment, just like any other experiment. We started with a great hope that it will be a grand success. It depends on us. There may be some hiccup, including today, so bear with us. And certainly, if you have ideas to improve this, please let us know, and we will improve this. So with that introduction for the seminar series, I want to talk about our inaugural speaker. I said that young speakers, Andrea is certainly young. Those who know him, he's young at mind always, and he's going to give the talk today. He's the Distinguished Professor of Mechanical Engineering at University of Houston and Berkhoff Professor of Applied Physics at University of Twente, and he's an NAE member. He's a well-known leader in multi-phase flow. He doesn't need any introduction, but I got to go through this motion. He's known for his seminal work on bubbly flows, cavitation, average formulations, you name it. He's the editor, he was the editor-in-chief of IJMF. He's the editorial board of Annual Review of Fluid Mechanics. He has many awards. I'm not going to go over all of them, but the significant one is the highest award in fluid mechanics community, which is the Fluid Dynamics Prize by the APS DFD that he got 17 years ago. So in 2003, 18 years ago. In 2014, he won the Euromech Fluid Mechanics Award. And then I will skip all the other awards and I get to it. He has two really outstanding books. If you haven't bought it, go buy it. They're really great books. He also got the Lifetime Award from Japanese Society of Mechanical Multi-Phase Flow in 2001. So today he's going to talk about, you may think that he's going to talk about fast cars, but he's going to talk about bubbles, fast bubbles. They're fast, dangerous, and unstable. So he's going to talk about that. Andrea, I will mute myself and I will turn off the video, and floor is yours.
Okay, well, good morning, good afternoon, good evening, everyone. And so let me start by thanking the committee for this invitation, which is a responsibility, but an opportunity as well. And I am particularly grateful to Bala for including me among the young researchers. I don't know about that, but anyway, I'll see what I can do. So, but also I want to congratulate Bala and Alfredo Soldati for the idea of this seminar series, which is, it's a great opportunity to highlight the vibrancy of our discipline, which is such a significant component of the broad field of fluid mechanics. And then also, I am very impressed by the way in which they have taken lead of the journal and the progress that it has made, and how it has been sort of continued on this upward trajectory. I worked very hard for a decade trying to, to resuscitate it, to put it back where it belongs. And I am delighted to see that this work has not been in vain, and that the new leadership is as competent and as successful as one might have hoped. So let me start sharing my screen. So I tried to come up with a catchy title, and you let me know whether I have been able to put some substance under it or not. So what the plan specifically is to talk about three topics on Taylor bubbles. One is how to make Taylor bubbles faster. Then I'm going to talk about the dangers of gas kicks in the oil industry. Since I'm in Texas, this is a problem that has come into my consciousness in the last few years. And then I'm going to address another topic that I worked on some time ago, but I think it's kind of interesting nevertheless. Okay, so let me get started with this idea of faster Taylor bubbles. Now, the founder of International Journal of Fluid Mechanics of Multi-Phase Flow was rather reluctant to submit papers to his own journal because he did not want any, any favoritism in the treatment of his papers. And I have been doing the same thing. I don't want to embarrass my colleagues by asking to get a paper accepted when the reviews are bad. So I sent this particular paper to the Journal of Fluid Mechanics, and this is a joint work with an associate research scientist, Guanzhao Zhu, who is a very gifted computational scientist and has been really instrumental in much of the work that I'm going to talk about. So as I said, we submitted this to the Journal of Fluid Mechanics, and one of the reviews that came back is the following. I failed to see in this study any new substantial contribution to the bubble propagation along vertical tubes. Regretfully, for reasons specified above, I cannot recommend publication of this manuscript in the Journal of Fluid Mechanics. So you see that I would have put my friends in a bind if they had received a review like this for my paper. But the other two reviewers were pretty enthusiastic, so I suspected that the paper will be accepted. But in any event, you will see what I'm talking about, and you will decide whether there is any merit in this study or not. So as many of you will know, this subject, the basics of this subject goes back many, many years. And both Dumitrescu and Davis and Taylor showed that the rise velocity of a Taylor bubble is basically only dependent on the diameter of the tube. Now, this is only true if the Reynolds number is large enough and so forth. But the idea is that basically the rise velocity is critically influenced by the diameter of the tube. But I talked about this with Dan Joseph several times. And as he used to say, the problem is quote unquote solved, but not understood. Let me just run over something that many of you are quite familiar with, just to remind you of why we see, why there may be things that still warrant some investigation here. So what did Davis and Taylor, and in a little more complete way, the other workers do in this topic? Well, they started out with assuming a potential flow in the frame of reference where the bubble is at rest. And then they introduced a brutal approximation of keeping only one term of this infinite series expansion. And then they, of course, had to deal with the kinematic condition, and they impose it near the bubble nose. And so this coefficient A1 becomes 1. And then they impose a dynamic condition halfway between the axis of the tube and the outer wall of the tube. And this way, they find that the rise velocity of the bubble is given by this. Now, this number 3 to 8 is a little off. Dumitrescu did something similar, but he kept 3 terms in the series. He got a better result. But in any event, this is really the background that we have on Taylor bubbles, more or less. With other people, of course, have done other work on this and so forth. But this is really the basic idea. So now, what is kind of paradoxical here, as was pointed out in a paper, International Journal of Multiphase Flow, by Funada is the first author, but the paper was really driven by Dan Joseph, is that there are several paradoxical features on this thing. So if the rise velocity is predicted without any dynamic force balance, just from the bubble shape. This is strange. Then the theory is inviscid, but the buoyancy force is a constant. So evidently there must be dissipation. Otherwise, the velocity of the bubble should change, but there is no trace of dissipation. Where is it? And then there is this very remarkable property that the rise velocity is independent of the length. But you would expect that the buoyancy force to be proportional to the volume. So what happened to the Archimedes principle? And finally, the rise velocity is independent of how the gas is introduced. Is the bottom of the tube open, or is it closed, and just the gas is introduced at the bottom, or what? So there are other paradoxical features, but these are pretty major ones. So if you look around, there is, however, information in the literature that gives you an idea of what might be going on. Let me just mention one paper by Clanet and others, and they did experiments with polygonal tubes, and they found that the rise velocity is proportional to the square root of the perimeter of the tube. And for a given cross-section, we must increase the perimeter to increase the velocity. And that is an interesting idea. So in this graph, unfortunately, the image may not be that sharp. This is the rise velocity as for bubbles in rectangular and square channels, and it is plotted as a function of the square root of the perimeter, and you see that there is a reasonable correlation as a straight line. So now, why would that be? Well, if you think about it, there must be something like this going on. So suppose I have a bubble that rises, and T1 and T2, well, there is space around the bubble, behind the bubble, that must be filled. So the liquid that fills this space must make its way from above the bubble to behind the bubble. And, but this is, so how does this happen? Well, since the bubble pressure is essentially constant, there cannot be any pressure gradient in the film. And because there is no pressure gradient in the film, there really is no communication between the top and the bottom of the bubble. So you can think of having this bubble being a solid object, and you attach a string here and you pull. Well, what happens? Well, if you pull harder, there will be the pressure below the bubble will become below the object will become less, and this lower pressure will increase the flow rate of liquid from around the bubble in the film surrounding the bubble. But this is not possible if you have a real bubble instead of an object, because the pressure is constant along the bubble and it is constant in the film, so there cannot be a pressure difference between the top and the bottom of the bubble. So what happens is that the liquid is in free fall along the bubble sides. Of course, free fall in the sense that gravity is balanced by the viscous by the no-slip condition along the wall surface. But nevertheless, it is in free fall. Well, then we start to understand why the length of the bubble is not important, because if the liquid is in the liquid film is in free fall, whether the bubble is 10 centimeters long or 50 centimeters long, free fall is in free fall. You have this equilibrium between the gravity and the no slip, and that is the amount of liquid that can go from the top to the bottom of the bubble. And this is what determines the rise velocity of the bubble. In other words, it's like filling a glass of water. If you want the water level to rise, well, the only way you can do is to add water from somewhere else. Well, this is what happens here. In order for the bubble to rise, you must add water. Just wait for this water to fall down the film and fill the space that is made available behind the bubble. Okay, so, and indeed, another indication of this fact in the paper by Clanet that I referred to a moment ago is the fact that this constant K decreases as the number of sides of the polygon increases. Why is that? Well, because if you have a triangular tube, well, you have relatively large channel for the liquid to go through. But as you increase the number of sides of the tube, well, these channels becomes smaller and smaller. Okay, so once you understand this, well, you start thinking and you formulate the following thought. So suppose that I can enlarge the gap between the bubble and the wall and the tube wall. If I manage to do that, would the bubble rise faster? So this is the question that prompted the study that I'm going to briefly describe now. Okay, so how can I enlarge the gap between the surface of the bubble and the surface of the tube? Well, an idea would be that we can put a cage of solid rods coaxial with the tube, and we can constrain the bubble inside this cage. So this is what we did. So, the Galilei number is not very much. The Morton number is too large, but this is because computation is not probably the best way to address this problem. The best way is to do an experiment, because computation, having these small wires, small rods, and resolving them with adequate gridding and so on, it becomes an expensive proposition. But nevertheless, what we try to establish in this paper is whether this principle works or not. And what is kind of remarkable is that this principle works well beyond our fondest expectations. So this horizontal line is the rise velocity of a bubble with those parameters that I had before in a tube without the cage, in a normal tube. Okay, now if you put in that cage, you can increase this velocity from about, let's say, 0.36 to about 0.55. So you are increasing the velocity by well more than 50%. Now, this is not the upper limit. We don't know what the upper limit is, and probably an experiment would be a more suitable way to do this. But this is what we can do. And these various points here are different cases that I will briefly talk to you about later. But in some cases, it doesn't work. These bubbles actually rise slower than in an empty tube. This bubble, which is a rather remarkable situation, I will show that later. All the other cases, the bubbles rise faster. Okay? So let us look into the fluid mechanics of this. And so this is a graph of the pressure along the tube. Remember, these yellow lines would be the rods that constrain the bubble. And so the pressure is hydrostatic above the bubble, is hydrostatic under the bubble. This purple line is a line in the gap between the bubble and the wall of the tube. So as you approach the bubble, the pressure in this gap starts to fall. Well, this is obvious because liquid must be expelled out of the core of the tube into the channel on the side. And this red line is the velocity in the radial direction. And as you see, indeed, this velocity becomes rather positive and relatively strong in this region where the liquid is pushed out of the core of the tube. Whereas the axial velocity, now this is axial velocity along a line, as I said, in between the rod and the surface of the tube, the axial velocity becomes strongly negative as the liquid falls. And then, and the pressure here, the dashed line is the pressure along the axis of the tube. And so it is constant inside the bubble. And then it is lower near the bubble top, because you need to have this pressure gradient that pushes the liquid out of the core, and then it becomes instead higher near the bubble bottom because you need to push the liquid back. Okay, and we can also look at horizontal profiles, and you see, let's look at, these are the pressure profiles. So the solid line is above the bubble. And as you see, the pressure is has a certain constant value above the bubble, and then it has a lower value in the gap here. And then if you go at this level here, the pressure has increased in the core of the tube, and it is much lower in the gap, in the annulus. And it is this pressure gradient that pushes the liquid out of the core of the tube into the annulus. One thing that is kind of remarkable in this pressure distribution is that, as I pointed out earlier, if you have a normal bubble in an empty tube, the pressure along the bubble should be constant. But here, because we have this obstacle to the liquid motion caused by these tubes, what happens is that you have a pressure gradient. The pressure above, near the top of the bubble, is less than the pressure near the bottom of the bubble. And we will see that there are consequences of this phenomenon. So, well, this is another view of what is going on. So this is a radial velocity on the left. You see you have a high radial velocity as the bubble rises and pushes the liquid out, and you have a negative velocity behind the bubble when the liquid is pushed from the annulus into the core of the tube. And the axial velocity is positive above and below the bubble, and it is negative along the channel, the annulus, where the liquid must go down to make room for the bubble. So, as I said, there is a pressure gradient along the bubble. And this pressure gradient has the consequence that if you have a very long bubble, then the pressure at the top is less than if the pressure is, if the bubble is not as long. And because of this, since what holds the gas inside the cage is surface tension, well, if you have a stronger delta P, then the surface tension will allow the gas to shoot out a little more out of the cage than if you have a smaller delta P. Okay, but this is what happens. And this is an important facet of this phenomenon, as we will see later. So now these are two other examples. Now this is, in this case, the cage is much denser. And so as you see, the gas does not stick out as much. And also there is a significant effect on the top of the bubble. And this instead is a net in which, in addition to having rods in the vertical direction, you also have rods in the horizontal direction. And this actually looks, it is probably better because in this way, in surface tension has two radii of curvature to help you instead of having only one radius of curvature, as happens essentially here. Another example here is what happens if you shrink the annulus. If you make it thinner and thinner, well, the bubble becomes smoother, the pressure gradient becomes smaller, but the rise velocity turns out to be not as strong. Now, as I said, if what holds the bubble into this cage is a surface tension, and if the rods are too thin, the gas large, surface tension cannot hold the bubble. And so this is one case that is simulated in which you see this phenomenon. In this case, the bubble does not reach a steady state, but actually keeps accelerating. And so we were not able to include this in that graph of rise velocity. But a very interesting thing is that same approach works if you put the gas outside. You see this in this particular case, the rise velocity is quite large. Now, this may be kind of useful if you think of a device to remove vapor. If you boil a liquid, the vapor, of course, will be generated on the wall of the tube, and therefore it might stay outside. And if you want to remove this vapor faster, either to feed a turbine or perhaps to limit the danger of burnout, well, would be interesting to push this vapor out of the way as much as possible. And this is what can be achieved in this way. Now, there are other ways to increase the rise velocity of bubbles, of course. Well, one obvious way is to use a bigger tube. Well, that's trivial. But another interesting way is to tilt the tube a little bit. If you tilt the tube, you have you lose axial symmetry. And what happens is that the bubble is pushed towards the upper part of the tube surface, and the gap between the bubble surface and the tube wall gets larger, and that's why the bubble rises faster when you tilt the tube. So we tried other implementations. So another thing you can do is to make holes in the wall of the tube, right? Something like this. Well, well, we were not very successful in this with this arrangement. As you see, the velocities that we find, of course, these velocities are predicated on the diameter, on the outer diameter of the tube, not the inner diameter of the tube, but the velocities are actually smaller than in an empty tube. And it could very well be that this is because in our numerical simulations, we could not use a large enough Reynolds number, and therefore viscous effects here are so strong, perhaps, that they stop the falling of the liquid into this channel. So we don't know if this works or not, but in any event, we thought that this was an interesting possibility to look at. Okay, so this then concludes the first topic of this presentation. And let me move on to the second topic. Now, this is the dangers of Taylor bubbles. And this work is joint with Dr. Zhu, and also the second paper with other colleagues at the University of Houston. So let me just, some of you may not be familiar with this idea, so let me remind you of a major accident that happened about a decade ago. Actually, it is the anniversary today. It was April 20 of 11 years ago. There was this drilling rig called the Deepwater Horizon, which essentially exploded on April 20 in 2010. And this was located, this is the promontory where New Orleans is, and this is where the Deepwater Horizon was anchored. And that's where the accident happened. And there were, as the witnesses said, at about 10 p.m., the rig unexpectedly began to shake, and the loud surging noise was accompanied by natural gas, drilling mud, and seawater that shot high up the floor of the drilling ship. The gas exploded, and the rig was engulfed in flames. It was a tragic event. There were 11 dead. There was, for nearly 3 months, there was an uncontrolled oil leak at the bottom of the ocean, and there were 500,000 cubic meters of oil that were spilled and contaminated the water and beach and the environment for a long time. So what happens is what people call the kicks in the oil industry. So when you drill an oil well, what you do is you push down into this, called the drill string. You push down a heavy liquid that is either a suspension of sand and water, or a suspension of oil and water. And the role of this liquid is several roles. One is to lubricate the drilling bit down here. The other is to maintain a high pressure at the bottom of the well. And the third role is that when this drilling mud, as it is called, gets back up on the outside of this riser, it carries with it the cuttings that the drill bit generates at the bottom of the well, at the front of the well. Now, what can happen is that for unexpected reasons, this drill bit punctures a region of the rock where the pressure, for some reason, is much higher than elsewhere. When that happens, you have an inflow of fluid from the formation into the riser, and this fluid rises. Now, if the fluid is liquid, not much happens. There is no particular problem. But if the fluid is gas, then you can get a very major effect, and that is what is called a gas kick, as I was saying before. So let me give you let me first show 2 simulations done with open foam. Now, one thing that you need to appreciate here is that the base of the bubble rises at a constant velocity, and that goes back to what we were talking about before. But the top of the bubble rises at a much faster velocity, or rather, I should say, can rise at a much faster velocity. Okay, and we'll see the implications of this in a minute. So what happens? Well, let me give you first a very simple explanation. Now, this is too simple, really, in some way, but I will add to it as we go along. So what happens? Suppose that you have a 1 meter long bubble at 16 meters depth. By the time the bubble has risen to 800 meters, well, more or less it is about 2 meters long because the hydrostatic pressure has fallen. And when it has risen to 400 meter depth, the bubble now is 4 meters long, but the time between 800 and 400 is about half the time between 1600 and 800. So when the bubble has gone from 400 to 200, well, now it is 8 meters long, and the time it takes is a quarter. And so you see what happens when the bubble is at 100 meters depth, it is 16 meters long, and it in 1/8 of the time. So notice that what must happen between 200 and 100 meters, this bubble must expel 8 meters, it must expel from the top of the riser a column of liquid which is 8 meters long, right? Because the bubble will expand. So this is then, it gives you an idea that as the bubble rises and it expands, the liquid that must accommodate the expansion of the bubble must come out from the top of the riser faster and faster, because the time it takes for a bubble to halve its depth becomes smaller and smaller. Okay, now this is one of the ingredients that cause this very rapid ejection of liquid at the top of the riser if you're not careful. But there is actually another phenomenon that is an instability. And the way in which one can explain the instability very simply is the following. Suppose that you have this gas inside the well, let's say, and you can assume the first approximation that you have an equilibrium between the pressure inside the bubble, which is given by this, P0 and L0 are the initial pressure and initial length. This is just PV equal to constant. And the pressure at the top of the bubble, which is given by the pressure at the top of the riser minus, or rather plus, the hydrostatic height, hydrostatic pressure here, right? So if you want to solve this equation, well, you can intersect the right-hand side, which is the blue line, and this right-hand side is what wants to crush the bubble. And whereas the left-hand side, which is the red line, is the pressure that wants to expand the bubble. And if you do this, you see you have two solutions. You have one solution here, another solution there. Now, these two solutions are very different, because if you consider this solution here, and you imagine the bubble getting a little longer, well, when the bubble gets a little longer, the crushing pressure becomes much bigger than the expanding pressure, and therefore this particular equilibrium solution is stable. But on the other hand, if you look at this solution and you imagine expanding the bubble, well, a little bit, then when the bubble is expanded a little bit, the expanding force is much more powerful than the crushing force, and so the bubble will continue to expand. Because of this, this solution is unstable, whereas this solution is stable. Now, what happens as the bubble rises? Well, as the bubble rises, the two solutions get closer to each other. And at some point, a situation is reached in which the two solutions coalesce, and this solution, and this single solution becomes unstable. Now, this may or may not happen. It depends on the particular parameters, but this is really, these two phenomena are at the root of these devastating events of gas kicks. One is the fact that the bubble expands more and more, faster and faster, because it rises and the hydrostatic load gets decreased. And second, you have this instability that can add let's say, physiological expansion of the bubble can make it expand much faster because of this instability. Okay, now we did this study using the time-honored drift-flux model. It's a numerical study, and it was tricky though, because it turns out that for the situation that we had in mind, this model is stiff. So, it resists simple-minded applications of numerical methods. And so, well, most of you will be familiar with this model. Well, it consists of two continuity equations. One is for the gas and the other is for the liquid. Liquid density is assumed constant. There is a single momentum equation in which U is the combined velocity of the gas and the liquid. And then you have closure relations or considerative relations. With this V is a drift flux velocity. And the PdZ would be given in terms of some pressure drop due to turbulence and viscosity. So we have done simulations with this model, and these simulations seem to be reasonably accurate. These are data from the literature that we found. This is actually volcanology literature, which is kind of interesting, because the same phenomenon that causes the gas kick damage in the oil industry is supposed to cause these, so they're called the strombolian eruptions of volcanoes. And so these volcanology people did an experiment, and so they had a tube top that was open to the atmosphere. Actually, the pressure was kept low at the tube top, and they recorded the rise of the bubble base, the rise of the bubble top, and the rise of the free surface of the water in the tube. And as you see, our calculation seems to catch what is going on reasonably well. But let me show you some predictions. So what we did, this is a typical example. We take a 1 meter long bubble, and we release it at a kilometer depth. And this line actually is two lines. The blue line is the top of the bubble, and the red line is the bottom of the bubble. And as you see, for maybe 45 minutes, nothing much happens. But now let us focus on this particular time interval, which is in the right-hand side image. So you see here that the top of the bubble starts moving faster than the bottom. And now notice this happened the last 3 or 4 minutes. Okay, now, as I said, for 45 minutes, nothing happens. Okay, the last 3 or 4 minutes, this is what happens. But what is striking is what happens in the last 30 seconds. The last 30 seconds, what happens is that the velocity goes from the velocity of the liquid at the top of the riser goes from a few centimeters per second to more than 10 meters per second. Okay, notice these are seconds, and these seconds are 25 seconds about, and they happen 45 minutes after the gas first enters the bottom of the riser. Now, evidently, if you do not realize that something's happening in your riser, that you have gas and potential danger, by the time you start realizing what is happening, it's way too late, and you cannot take any mitigating action. And this is actually what happened in this Deepwater Horizon accident. There was an undetected gas kick that rose undetected in the riser, and it went unstable and started to eject this column of gas and hydrocarbons at the top of the riser, and there were sparks around, and so this this material burst into flames, and with the tragic consequences that happened. Okay, so what does the oil industry do about this? Well, let me let me skip this. Well, the current methods of kick detection are rather pitiful once you realize that the extreme rapidity of the event. So the pit or the pits are the reservoirs for the mud. So they look at the amount of mud in the pit, and if the amount of mud in the pit starts rising, well, that means that there is mud ejected from the top of the riser, and therefore something untoward is happening. Well, yeah, that in principle is correct, except that the pits are very large, and in order to appreciate that their level is increasing, you have to wait a long time. Also because, as I said, the ejection of liquid from the top of the riser is actually pretty slow until all hell breaks loose. Okay. Well, you can also look at delta flow. This is a difference between the mud that is pumped into the drill string and the mud that comes out from the riser. But again, you can have compressibility effect. You can have other reasons that cause the difference between the two flows. And therefore, this is imprecise, and it also takes a long time. So one thing that an outcome of our work was a new method for gas kick detection. Now, speaking to a multi-phase flow audience, I must recognize that this idea was actually already implemented in our community, but for different purposes. It was implemented to detect flow regimes, different flow regimes in a two-phase gas-liquid flow. And so they looked at the pressure difference between 2 points along the tube to decide whether it was bubbly flow or slug flow or annular flow. So now if you look at the pressure, suppose that this is your riser and you have a few pressure sensors arranged along the riser. And if you focus on one of these pressure sensors, well, the pressure remains constant for a while. When the bubble starts arriving, however, the pressure starts falling because now above the sensor, you have gas in addition to liquid, and therefore the hydrostatic load is less than before. So the pressure starts coming down, right? So this is what happens for all these pressure sensors. Now, this is a signal, of course, that tells you that there's something happening, but there is a better way to exploit this signal, and that is to look at the pressure difference between pairs of sensors. So as long as the bubble is under, for example, this particular pair, then the pressure difference will be something. In this simulation, it was an atmosphere. When the bubble starts arriving, well, the bubble penetrates past the lower sensor, and therefore the pressure difference starts to fall. And then as the bubble rises between the two sensors, it expands, so the pressure falls again. And as the bubble passes the top sensor, the pressure recovers. So this is a rather unique signature of the pressure difference if you have gas between two sensors. And so we did a little demonstration, rather our colleagues at the University of Houston did a little demonstration. This is a tube. There is the bubble is injected at the lower tube, and it is rising, and there were pressure sensors along the tube. And what they see is that when you inject the bubble, there is a mess. So this is a pressure as a function of time as measured by the various sensors along the tube. And when you inject the bubble, you get a mess of oscillation because the gas was pressurized. So you get basically oscillations of this bubble as it rises. But in spite of these oscillations, if you look at the pressure difference, you see exactly that characteristic pattern that I showed before, that the bubble rises, passes the first sensor, the pressure difference starts falling, and then as it passes the second sensor, the pressure difference starts rising. Okay, so this is a piece of work that has generated some interest in the oil industry, and we will see what happens with it. So let me come to the last topic, which is an instability of Taylor bubbles. And what I'm talking about is the fact that if you have a Taylor bubble rising in a quiescent liquid, well, you have what everybody knows. But if you have the liquid is in downflow, then the bubble is not axisymmetric anymore, but it develops a nose that hugs one of the walls of the tube. Okay, so I got curious about how this would happen. This is work that I did with a former student quite some time ago. I got curious about how this might happen, and so I did the following thing. So I basically followed the work of Taylor and others, but in particular the work of Collins, who used a viscous flow for the downward flow in the tube, but then they introduced a potential model to account for the bubble. So it is a hybrid, it's an unholy alliance between viscous and inviscid tools of fluid mechanics, but they were able to find in this way something that is very similar to the drift-flux model. So, and this is, so as G.I. Taylor and as Dumitrescu did, they took the stream function and they brutally killed this summation and kept only one term. Okay, and if you do this, and then you impose the dynamic boundary condition on the axis of the tube, you come up with a prediction of the rise velocity of the bubble as a function of the velocity of the liquid in the tube. So if to the right of this vertical line, the velocity of the liquid is positive, so this is co-current flow, and the bubble happily rises and rises faster than the liquid velocity, as is well known. When you start pushing the liquid down the tube instead, that is, the velocity becomes negative, for a while the velocity of the bubble remains positive, but then at some point you're pushing the bubble down in this way. Okay, and this is really you can do this with the drift-flux model, and this works. So we tried to understand the stability issue. And one thing that put us on the trail of the possible answer is the fact that if you have concurrent flow, the bubble is pointed, whereas if you have a countercurrent flow, the bubble is much flatter. Okay, so we will see that this is really at the root of this instability. So, well, what did we do? Well, we did what other people did. We married the viscous flow in the tube with a potential flow approximation for the bubble shape. So this, you see, if you have this factor, gives you a dependence on the angle around the cross-section of the tube. So if m is equal to 0, you have an axisymmetric bubble, but if m is non-zero, then the cross-section of the bubble is deformed. And in particular, what is important is m equal to 1. If you put m equal to 1, then what you can simulate a bubble that would normally be the axis concentric with the axis of the tube. If you put m equal to 1, you find a bubble that has the axis displaced from the axis of the tube. And so you can account for this deformation that I was interested in, right? This deformation from axisymmetric to a sideways distortion of the bubble by doing this, introducing a perturbation like this. And what we find is, I don't want to bother you with the details. We find an eigenvalue problem in which everything depends on time according to an exponential. And this lambda is the eigenvalue. And of course, if lambda is positive, then the system is unstable. So what I show here is lambda non-dimensionalized somehow as a function of the velocity in the tube. So now I have several lines here, and this depends on how many terms I keep in the series. I don't really want to bother with you with the details. Let me just point out that these curves in this region come more or less together independent of how many terms I have. And here is the critical region, because this is where lambda goes from negative to positive, which means that the bubble, when lambda is positive, the bubble axis becomes unstable. Okay, and now experimentally, turns out that this instability happens when the velocity of the liquid is negative in this range, so it should be about here, and so you see that our prediction is not that far off. Okay, so indeed we do find an instability of the axial symmetry of the bubble when the liquid is downward. But the question is why? But actually, there is a better question. Why is the bubble ever stable? In the end, you always have a Rayleigh-Taylor instability, right? We have the gas that is light under the liquid that is heavy, and therefore, why is the bubble ever stable at all? Why doesn't it rain through the roof of the bubble? Well, there are several reasons. One is that the perturbations that are formed on the bubble surface, as they propagate around the bubble, get stretched. And because they get stretched, their amplitude goes down. And so this is a way to kill the effect of the perturbations. Other perturbations that are not stretched might be convected around the bubble. Well, they have a limited time to grow, because if the velocity here is too fast, well, the perturbation will just be swept around and be gone. And finally, of course, you get Rayleigh-Taylor in full near the top of the bubble, but around the side of the bubble, Rayleigh-Taylor is less, because what matters is the component of gravity normal to the bubble surface and not the total gravity. Okay, so these are three stabilizing mechanisms of Taylor bubbles, or actually also of spherical cap bubbles in a liquid. Okay, now what happens if you have a downward flow? Well, in a downward flow, you see you have the total delta P, which is made of a gravitational part and the viscous part that you need to impose to push the liquid down. The downward flow requires a delta P that is opposite to gravity. And as a consequence, the fluid relative velocity is smaller, and therefore the interface flattened, as I showed before. The stretching of the perturbations becomes weaker, and the perturbations have more time to grow. And so this is what happens to the bubble shape. You should focus on the blue line. As I said before, if the velocity of the liquid is up, then the bubble is pointed. If the velocity of the liquid is zero, quiescent liquid, the bubble is less pointed. And if the velocity of the liquid is down, the bubble becomes less and less pointed. And so what are the consequences of this? Well, the Rayleigh-Taylor instability is strengthened because you have a flatter surface, you have a lower velocity, and you have this stretching decreased by the physics of the flow. Okay, now let me conclude the presentation, remind you of three topics I addressed. One is that the caged Taylor bubbles rise faster. The other one is that there are dangers when a Taylor bubble enters the riser in a drilling operation, because you have this velocity of ejection of the hydrocarbons out of the top of the tube that can go from centimeters per second to 10 meters per second within a space of maybe 10 or 20 seconds. And if you do not realize that you have gas in your riser, well, you are in very serious, indeed, in mortal danger. And then the last thing I talked about was the stability of the axial symmetry for Taylor bubbles in countercurrent flow. And I tried to explain how and why this axial symmetry becomes unstable if you have fluid pushing down and flattening the bubble top. And with this, I will stop, and I'll be happy to answer any question.
Andrea, thanks for a very interesting talk. I know that when someone moves to the state of Texas, the oil industry owns you. I now realize that that is indeed true, that you're working for the oil industry.
Okay.
The floor is open for questions. You have two modes in which you can ask questions. You can unmute yourself and ask the question, or you can post the question on chat and I will read that question. Okay, so please feel free. Maybe I will start the question, Andrea.
Yeah.
So when you talked about this cage, sometimes not only the speed, but the rate at which you move the volume of the bubble is the most important one. So if you're given the outer diameter, and if you put the cage, you reduce the diameter of that bubble, it moves faster. So is there any optimization in terms of a volume that is moved per second kind of?
Well, you know, as I said, what we tried to do here was just to explore whether this idea had any merit or not. But we cannot really do simulations for a liquid like, you know, low viscosity liquid like water using, you know, a small enough rod to construct our cage. So, you know, we do not really know what are the limits of this technology. But I agree entirely with you that, you know, that what matters is the volume. So yes, indeed, you make it faster, but you also make it smaller. So, you know, that is an optimization question in some way that we do not feel equipped to answer with the tools that we have. I think that what is needed here is a nice experimental program. And if I had to design an experiment, what I would do, I would use a net instead of rods. I would use a net, a relatively fine net, in such a way that the gaps are small and surface tension can hold more easily the gas. And that is how I would build the experiment. And then once you, and this is not all that difficult in the sense that you can just make this net, you can hold it with in a frame, and you all you need is actually is a tall lab, right? That's what you need. But it should be a fairly straightforward experiment. You know, nothing is straightforward, of course, but it should be a fairly straightforward experiment. And I can see that an optimization of this phenomenon can be pursued more efficiently in the experiment than in the computation. But I agree entirely with you that this volume rate is very important. I just was very curious to see if this intuition had any value and bore any fruit, or it was just a silly thing that would never work.
Okay. We have Oscar Rodriguez, a question from Brazil. Oscar, go ahead.
Thank you very much. First of all, I'd like to thank the editors of IJMF for this excellent idea of promoting this series of seminars. Excellent idea, and thank you very much for that. And also, Professor Prosperetti, very nice talk. I thank you very much for that. Regarding the caged Taylor bubble case, very nice and interesting topic. I was wondering whether we could do an analogy to what is going on in the current Brazilian offshore production scenario. There are in Brazil many mature fields, offshore mature fields, in which there is a lot of production of water. So it's actually a three-phase flow. So we have gas, we have water, and we have oil. And this oil can be quite viscous, relatively speaking. So sometimes some ideas to increase the Taylor bubble velocity would be to use some chemical products to actually invert the phase. So a water-dominated flow, a water-dominated three-phase flow would invert to an oil-dominated three-phase flow. So in that case, since the oil is a much more viscous phase in comparison to water, actually the liquid holdup would increase significantly, and then actually the void fraction would diminish. So that would imply in a faster Taylor bubble. So I would please, I was wondering whether this kind of phase inversion technique could be a possibility in your view to also to increase the Taylor bubble velocity on average.
Well, so basically you're talking, this phase inversion would be, so this idea of lubricated pipelining that Dan Joseph was so fond of, right? To coat the solid surface with a low viscosity liquid in such a way that the no slip condition doesn't kill you. Now, you know, in principle, I do not see any interaction between this cage idea and what you say. So if you have an emulsion of oil in water, and the continuous phase is the water, well, then reduces the friction against the wall of the oil, and the Taylor bubble would be a Taylor bubble mostly of gas in water, with, let's say, dirty water, or in an emulsion instead of pure water. But the crucial thing is surface tension. Now, it could be that some of the oil components migrate to the interface of the gas and reduce the surface tension. Now, if that happens, well, then there's a problem, because without surface tension, without a strong surface tension, you cannot really contain the gas in the cage. And so that might be a problem. I don't really know if there are surface active substances mixed in the oil that you are referring to, but if there are, then there may be a problem. And in this sense, you know, your question is interesting, but needs to be, you know, as usual, the devil is in details, and you need to see if the surface tension of the gas would be affected by the arrangement that you are referring to.
Andrea, thank you. We have two questions that are related. I'm going to read them for you.
Okay.
The first question is says, caged Taylor bubbles rise faster. Is this conclusion valid in general for fluids with different Morton or Edwards number? In a similar question, Marco Marengo from UK is asking, he's suspecting that surface wettability of the rods, which you right now talked about from a surface tension point of view, will have an effect. Can you comment on that? Those were the two questions that I combined.
Well, you know, these are both interesting questions, and yes. So addressing first the effect of parameters. Well, as I said, because of computational limitations, we could not simulate water. And for water, the Morton number is 10 to the minus 12. So, you know, what we have here is a rather fairly viscous fluid, a relatively low Reynolds number. Yet what we find is an effect that is pretty strong. So now the basic principle is that no matter what liquid you have, you always have this limitation that what limits the rise velocity of the bubble is the relocation of the liquid from above the bubble to below the bubble. And because you always have a zero pressure gradient along the bubble surface, you can, the rising bubble can never talk to the liquid under it in such a way as to pull more liquid down. So no matter what are the physical properties of the liquid, the fall of the liquid along this film, which is, I stress, a fall that is totally established by a balance between the no slip at the wall and gravity, there's nothing else going on here, you always are limited by that. So any way in which you can increase this flow rate will give you a bigger rise velocity of the bubble. Now, of course, if you have a very viscous liquid, it could very well be that it is so viscous that this adding these solid rods on the surface of the bubble around will increase the viscous dissipation so much that the effect will be lost. It will actually be counterproductive. We don't know, and that is conceivable. So, but if you have normal liquids that you might worry about, well, I think the effect should be pretty robust and should be there. Of course, dependent on surface tension. If the surface tension is too low, maybe this trick doesn't work. Now, coming to wettability, which is, I think, an excellent question as well, is, of course, crucial. If these simulations that we have been doing, we have assumed a fully wetted solid surface, but there are lots of coatings available in the chemical industry, and so it should be possible to render many materials, many pairs of solid liquid, to make the solid fully wettable with respect to the liquid that you're interested in. And once you do that, well, then the affinity of the solid for the liquid becomes much less, and there is a thin liquid film around these rods that will protect them from becoming dry, from drying up because of the action of the gas. And once you have that, well, then a surface tension is instrumental in holding the gas where it is.
We have one more question posted on the chat by Surya Narayan. Again, a related question, again, goes back to cage-Taylor bubbles. The question is, what do you think would happen when instead of cages, we use a porous media? And also, how does the size of the cage compare with respect to the diameter of the tube? The second question is sort of related to the question that I asked, Andrea, is there may be an optimum. But the question of porous media is maybe related to the other answers, but you may have something to add to that.
Yeah, well, of course, no matter what you do, you need to push the liquid from the top of the bubble to the bottom of the bubble, right? So, that is requires that you have a flow, that this liquid flows somewhere. Now, if you have a porous medium on the outside, well, then that flow is very strongly hampered. So I would expect that it would be an excellent way to slow down the bubble, because then you need to wait for this very, very slow porous media flow to go down, and then the liquid goes to the back of the bubble in this way. So I would say that the porous medium flow would have a very strong adverse effect on the rise velocity. That would be an excellent way to slow down the bubble. Bala, can you help me with the second part of the question? I forgot.
The second part of the question was the diameter of the cage versus the diameter of the pipe.
Yes. Well, yeah, as you already said, yeah, that is an optimization matter. Now, we have done these several simulations using changing the parameters, and we have some limited experience on making the annulus narrower. So these two data points here are for a narrower annulus. So it looks like that if the annulus is wider, you have a better increase in velocity. Now, of course, if they make the annulus very wide, at some point, this increase in the rise velocity has to saturate, has to slow down. I mean, has to saturate and to become constant. So we haven't tried to do that, for computational reasons. And also because, as I said, this should really be investigated experimentally rather than computationally to be efficient in this research.
Any other questions from the audience? Please unmute and you can ask, because I don't. Oh, there is one question I see on the chat. Oh, I can't read this. This is in Spanish. Andrea, you might want to open the chat and or
Well,
someone.
I have no problem with the Spanish. Let me see. I need to.
It's in Portuguese, apparently.
Well, that is, close enough. That should be understandable.
But he translated. This is from Rigoberto Morales. It says, in some scenarios, the Taylor bubble can be a mechanism for the transmission of pressure. Can you comment on this and the scenarios where this can happen? And Andrea, this could be the last question because it's been an hour and 20 minutes, unless there are some burning questions people may have.
I am not entirely sure. So in some sense, the Taylor bubble short circuits the pressure, or rather impedes the pressure transmission, right? Because by preventing any pressure communication between the liquid above and the liquid below, you basically suspend the pressure gradient when you have a Taylor bubble. So as I showed in this graph, right, inside in the tube, you basically have a constant pressure in the region occupied by a Taylor bubble. So I imagine that there might be situations in which this is a useful thing to do. I am afraid that I do not know enough to come up with a plausible scenario, but I would be very interested in understanding this a little better. And if the person who asked the question is kind enough to send me an email, I would be very interested in what he has to say.
Okay, a last chance to ask questions. Okay, I want to, oh, well, then one last question came in. How about bubbles interact with drops in liquid medium? I don't know whether you want to say anything.
I mean, this you can write a book on bubbles interacting with drops. I'm not entirely sure, how to take this. So, well, I mean, Taylor bubbles are in some sense very, they belong to a different zoological species compared with normal bubbles, millimeter size bubbles. So, in Taylor bubble, yes, I assume it could interact with the drop in the sense that the drop might be stuck on the surface of the Taylor bubble and might be convective down as the bubble rises. Yes, that might happen, but I don't really have anything to say on this subject, I'm afraid.
If people have more questions, feel free to send emails to.
Yeah, absolutely. By all means, I'll be very happy to entertain more questions. They will be interesting and interesting things to talk about, to think about, and I'll be very happy to reply to you.
Andrea, thank you very much for talking on three excellent topics. And a great way to kickstart this seminar series. And we had attendance from just about every continent. Overall, I think there are about 200 people who attended overall. I see Alfredo join us. So everything went very well. And the next seminar is going to be on May 4th. All the seminars will be on Tuesdays. Please, we want to make this into a sort of an habit, at least for the next 2 years, so that people watch on the first and the third Tuesday of a month, provided it's not a summer or the winter, and that there will be a seminar. So the timing may change depending upon where the speaker is from. So we are trying to distribute the speakers between Asia, Pacific, Europe, and Africa, and the Americas. Okay, so with that, I want to bring this seminar to a closure. Alfredo, you want to say something? Please go ahead.
I just want to thank you all the other organizers for having organized such a nice thing. I want to especially thank Andrea for the great talk, which I missed for the first part. And the audience was tremendous because they really liked the talk of Andrea and the initiative. And we keep going every 2 weeks. Mark it on your calendar every 2 weeks. Thanks a lot, Andrea. Thanks a lot, Bala. Thanks a lot to all.
Oh, thank you also, Alfredo. You couldn't join today earlier, but you were part of this whole organization. Thank you all for coming. And I really am so thrilled that we got about 200 people to attend.
Yeah.
And our community is alive and vibrant, and maybe we can showcase more work like this. So that brings this meeting to a closure. Andrea, you want to say anything, or I will?
So I would like to thank you and the audience for especially people in Japan for whom it is 2 a.m. Of the night. And so I hope they have a good night's rest. And thank you for the question, and thank you for the attention.
Thank you.
Thank you all.